Hello everyone, I am Shweta Lokhande, a PhD student at the Srishti Lab, IIT Bombay in the Environmental Science and Engineering Department. And in this video, I will be walking you through one of our recent publications in the Journal of Environmental Management on a method for appropriate sizing of sewerage zones from sustainability and resilience perspectives using scaled decentralization. Not all of us are researchers who are going to read this research paper, right? And hence, I have come up with an explainer video for different stakeholders who can understand the significance of the present research. And in this video, I will be discussing the need for the research, the concept of optimal scale for infrastructure, the novel method which we have developed for computing the optimal scale of sewerage infrastructure for cities, how the method can be used for planning new cities, as well as retrofitting the existing sewerage infrastructure in cities, and the policy implications and way ahead. As we are all aware, and every water, wastewater practitioner or environmental engineer might be aware that massive investments are happening in the sewerage infrastructure globally, and several cities are now on the verge of planning and designing the underground drainage systems. There is a high risk of inefficient resource utilization owing to a lack of consideration of the scale of implementing sewerage infrastructure in the absence of any decision support for the practitioners. And as a result of this, the urban local bodies have to face several challenges, such as low flows that are received in the sewage treatment plants, underutilized capacities, inefficient energy usage, and inappropriate technology selection. In this regard, the present research is vital in providing decision support regarding appropriately sized sewerage systems to prevent the underutilized or non-functional capacities of sewerage infrastructure in the future. One of our earlier works in water policy discusses the need for scaled decentralized infrastructure, and in this article, we have discussed the trade-offs across different scales, that is, trade-offs between the highly centralized and highly decentralized infrastructure from the perspectives of sustainability and resilience through different indicators. And considering which, we have proposed that the ideal zone for attaining sustainability and resilience lies somewhere in the middle, and it needs to be quantified. You can scan the QR code for a YouTube video on a detailed explanation and an illustrative video of the complexities of the sewerage infrastructure and the need for an optimal scale of implementing infrastructure. Alternately, you can also find the link to the video in the description below. So, the optimal scale of decentralization or the appropriate sizing of the sewerage zones, which also results in the size of the STPs for a given region. So these are associated with the scale of the cities, that is the amount of sewage generated in million liters per day in the entire city. For example, for a city with sewage generation of up to approximately 22,000 million liters per day, the proposed scale of decentralization is 50 to 80 million liters per day, which means that the size of the sewage treatment plants in this metro city can range between 50 to 80 million liters per day. In this research, this concept of associating the optimal scale of decentralization with the size of the city is expanded further, and a logarithmic curve has been fitted between the estimated sewage generation in the city and the size of the municipal STPs. And this is the equation for the logarithmic curve fitting, and this has been discussed further in the slides. However, a couple of quick points regarding the same. A nonlinear variation in the STP sizing is considered due to factors such as the differences in the scale of cities, the availability of funds, and skilled labor for infrastructure, which vary across the different sizes of the cities and localities. And although restricting the size of STPs for big cities implies large number of STPs, so basically, uh, when it comes to decentralized implementation of infrastructure, a common notion is that, but there will be too many STPs and a lot of operation and maintenance. Uh, However, in this case, especially for big cities, a dedicated team of urban local bodies can look after managing the multiple sewage treatment plants. Although this would require several resources or additional resources, it would surely benefit from the operational savings of maintaining the long and deep sewer networks of highly centralized systems. So the next question is then how to find the optimal scale for a given city. The prerequisites for data in order to use this developed methodology is very simple. The urban local bodies just need their past population data, and uh, this equation can be used as a decision support. A few pointers regarding the same. The starting point for equation is 20 million liters per day. That is, uh, two plants of 10, let's say 10 million liters per day are recommended for a starting size of the city of 20 mld. Why? Because of the scale of economies. As from literature, the factored cost per MLD for sewage treatment uh, reduces with increased STP capacity, and it somewhat flattens between 10 to 20 million liters per day. So it can be safely said that a sewage treatment plant exceeding 10 MLD capacity has attained the scale of economy, and hence the minimum size can be recommended as 10 mld, and hence for a city of a size 20 mld, two treatment plants of 10 mld can be adopted. The second pointer is regarding the maximum STP size, which in the present research has been restricted to 80 mld, with a key aim of facilitating water circularity within the city. So, in literature, plant capacities exceeding millions of population equivalents or PE are termed as mega centralization. And mega centralization come with its own set of disadvantages discussed in the literature. And from this perspective, we have chosen 80 mld as the maximum size, which somewhat comes around 1 million population equivalents, matching with that from the literature. Next, the logarithmic equation was chosen for curve fitting. Why? To account for the limiting sewage treatment plant capacity. So, as discussed further, to ensure the curves flattening, the data set from 2000 mld to 3000 mld was assigned the same value of 80 mld to limit the maximum size of STP. The primary reason being the severe disadvantages of highly centralized systems with respect to the deep sewer networks, and also to facilitate water circularity, as no further economies of scale are achieved beyond a particular size that can give additional benefits for the infrastructure. And lastly, up to 30% buffer for the proposed STP size has been considered to facilitate a proposed range rather than a single value of the optimal scale, because we recognize that there is a dynamic nature of a sewerage infrastructure and several trade-offs exist in various drivers, and hence there cannot be one size that can be suggested as an optimal scale, even after thorough research, because of the complexities of the sewerage infrastructure. And hence, we authors we do not imply rigidity while using the proposed STP sizes. However, and hence the we have adopted a range instead of a single value. Uh, Next, I will explain how this equation can be used for new cities through an illustration example for Hapur in Uttar Pradesh. for which the past population data was available from 1971 to 2011, and the population was forecasted up to 2051. So, the first step of the methodology is to forecast the city's population, up to which the sewerage infrastructure is to be planned. And this can be done using the popular uh, population forecasting methods such as the arithmetic increase, geometric increase, incremental increase, and the average of these can be taken for the design year of 2051, and this can be regarded as the design population denoted as P. Alternatively, for a particular city, depending on the context and the growth of that particular city, you can use a, a relevant or suitable population projection method to arrive at the design population. The next step is to estimate the future sewage generation of the city, which is denoted as by S, and for which the water demand, uh, which in the Indian context has been assumed as 135 LPCD, can be used, and a sewage conversion factor of zero point 0.8 has been considered. This yields the total size of the city, that is the sewage generated by 2051, as 334 million liters per day. In the next step, this S is compared with the starting size for using the equation of 20 mld. And since it exceeds 20 mld, equation 1, this has been used to calculate the proposed scale of decentralization, that is the suggested capacity C, which is which comes as 49 mld in this case. And since in the case when S is less than 20 mld, two or three STPs or more, depending on the urban settlement characteristics, such as the physiographic barriers and the topography of the city. So those can be assessed to recommend and propose the SCPs. Next, a buffer of plus or minus 30% is suggested, and it can be denoted as L and U for a given city. And for Hapur, this buffer yields the range of 34 to 64 mld as an acceptable range. And the last step is calculating the number of sewage treatment plants, which comes to 7 in this case. So a key significance of this number 7 is with respect to planning the infrastructure in a decentralized way. So at the planning phase itself, multiple land parcels, so 7 in this case, can be planned for sewage treatment, and this can avoid the bottleneck of land for sewage treatment in the future. Uh, Now, in this application, I will be discussing like how the same decision support of that equation can be used for retrofitting the existing sewerage infrastructure. So, in this case, the case of Pune, Pune has already has an existing sewerage infrastructure comprising of various sewage treatment plants, and the data from the STP inventory from the Central Pollution Control Board was used for this purpose. And for Pune city, like the total sum, like or the scale of the city was computed. The equation was used to compute the proposed range of the optimal STP capacity, which comes around 64 mld, and the buffer was used to calculate the lower and upper limits as 57 to 77, which have been plotted in this graph. And then apart from that, each point represents an existing STP in the city, while its location represents the scale. The shaded region represents the proposed range, that is the optimal STP capacity for sustainability and resilience. And the positive outliers indicate the tendency of centralization, whereas the negative outliers indicate the tendency of decentralized infrastructure. So the graph depicts that a large number of STPs are present in Pune city, uh, so which is good in a way, as the treatment is staggered across the city. And this high tendency of decentralization is observed, which can be used in the benefit to attain circular economy within the city, for which proper planning and planning of the infrastructure and ensuring a market for the treated wastewater would be required in the future. The second case talk is for the city of Mumbai. And this data has been represented in two parts. So, in the, from the size of the city, uh, the proposed STP scale has been arrived as 88 MLD, and 79 to 105 million liters per day is the proposed sizing. Now, as you observe, in the first part, this shows the existing or the under construction of the proposed SDPs, their capacity. And while the present research from a sustainability and resilience perspective denotes that around 88 to up to 105 million liters per day can be a good scale for the same. The existing STP sizes ranges from 500, 600 to even 800 million liters per day, which is mega fold times the optimal proposed scale. And hence, these STPs might face the consequences of or the have the disadvantages of highly centralized systems in future. On the contrary, Mumbai also has installed some decentralized sewage treatment plants at the building or the institutional scale, which are denoted here. As you can see, the capacities of these is less than 10 MLD, signifying a high, like extremely high degree of decentralization. The extremely low capacities of decentralized STPs are not suggested if the infrastructure is to be maintained by the Bombay Municipal Corporation, which means that uh, even if institutional or decentralized STPs at a building scale are prevalent, like they would sustain in the long run only if the buildings only if the building administration, the technology providers, and the residents, so they are actively involved in the uh, operation and the sustenance of the sewage treatment plant. From that operational and maintenance perspective, like instead of the extreme small sized STPs, uh, the proposed decentralized STPs of up to 80, like up to 80 to 100 million liters per day are suggested. So, such graphs can be plotted for other cities having STPs to gauge the appropriateness of scale for implementing sewerage infrastructure and accordingly retrofit the same. For more explanation or the interpretation regarding the usage of the equation, you can refer to the journal publication. Coming to the policy implications. So, in this table, for different project phases, how different stakeholders can take the actions and measures for implementing scale decentralization is presented. So, for example, in the planning phase, the city engineers or town planners can work towards deciding the appropriate size of the municipal STPs by considering the location specific characteristics and accordingly facilitate or reserve land for sewage treatment from a decentralized perspective. Then, in the design phase, the engineers and technology providers can work towards uh, researching regarding the optimal network layout and appropriate technology selection. And decisions can be taken so as to minimize the number of pumping stations in the city during the implementation. The engineers and practitioners can work towards constructing the STPs in a multi-phase manner, which can provide flexibility and adaptive capacity in the infrastructure. And lastly, during the operational phase, the municipal engineers or plant operators can in their quest for retrofitting actions, they can identify the large zones or extremely centralized zones and explore the possibility of acquiring land near the pumping stations that can facilitate even a partial treatment and tapping of sewage for decentralized treatment. So, as procuring land for sewage treatment is a bottleneck for sewerage infrastructure, as observed from field experience, uh, planning the decentralized infrastructure necessitates the availability of land parcels at multiple locations, for which an understanding of the number of STPs and their approximate sizing is important. And the present research is a step in that direction. Although there is a paucity of research on optimal scale, and due to this, the data used for the curve fitting is based on certain assumptions and field experience. Uh, it is a rigorous exercise to carry out a detailed quantitative assessment for multiple sustainability and resilience parameters, even for a small city. And replicating such field-based studies for large cities is surely highly resource intensive, and it might take several years to even generate a single data point in the on the assumptions that are used for the curve fitting. But we can't afford to wait because the time for action is now. And this research can be regarded as a starting point for optimal scale consideration, and in future evidence can be generated through more cases across India, and the data set can be modified. However, despite the modification of the data set, the methodology of the logarithmic curve fitting developed in this work can still be used for planning the new infrastructure or for retrofitting applications. Thank you. If you have any further questions regarding the methodology, the developed decision support, or need any assistance with using the same for your city, please feel free to reach out to us. And alternatively, we would also be happy to learn more from your experiences with respect to the challenges of the sewerage infrastructure. So, in that case, please reach out to us. Thank you.